Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento. This video is the beginnings of a series of videos on ellipses. Ellipses are conic sections, and if you haven't seen it, I have a video prior to this that discusses why we deal with conic sections and what they actually are. And it also kind of expresses my view on teaching conic sections. I think it's more of a requirement than something that most students need to go through. However, there are some great applications for conic sections, and specifically the ellipse. So let's go ahead and go through and talk about the various definitions involved with an ellipse. First of all, by definition, an ellipse is the set of all points in a plane, the sum of whose distances from two fixed points, called the foci, is constant. That sentence right there actually is the full definition of an ellipse. There's not much else to it. However, it doesn't really give you the impact of how to build an ellipse. So these, to the lower right hand corner here, you see an ellipse actually, and there are two points called, each is called a focus. Together they're called the foci. So they're the foci right there. And if you connect the string to each of those foci, and that string is of constant length. So in other words, you don't allow the string to stretch or anything like that, but you grab a pen and you go ahead and make the string taut. Then as you draw out along the edges, it creates an ellipse. Let me show you a better animation of something like that. So what you're looking at is Wolfram.com, specifically mathworld.wolfram.com. And this is the actual animation of how an ellipse is created. You have 2 points called the foci. You have a string, and the length of that string is a constant. And then you just grab a pen or a pencil, and you rotate around. As long as you keep the string taut, you should actually create an ellipse with your drawing. It's a very cool way to build an ellipse, and the official way to build an ellipse. And you could probably see right here on the left hand side, you can see this little image right here, and there are a lot of pieces to an ellipse that need to be discussed. So it's a bit of a trudge here to get through it, but we will succeed. So here we are, we're back at the actual definition. Again, we have those 2 points that kind of help us build the ellipse called the foci. The center of the ellipse is the midpoint of the line segment connecting the foci. So you're going to see my screen tear as I move up sometimes, and that's just because I'm projecting my laptop screen to my desktop to do this, and my internet sucks, and I do not understand why I need to go through the internet to do that. But anyway, the center is the midpoint of the line segment connecting the two foci. So if you look at that line segment right there, halfway between those two foci is going to be the center. So I'm just going to mark that right here. This will be our center. I'm not going to use the letter C for the center, unfortunately, because that's used for something else. After we've discussed the center, we now talk about the ellipse's vertices. Now, the ellipse actually has 4 vertices, and they're collected into 2 groups. The first group is called the major vertices, and then the second group is called the minor vertices. The major vertices are the 2 points of greatest distance from the center that lie on the ellipse. So here's our ellipse. The 2 points of greatest distance from the center that occur on the ellipse are actually these 2 points right here. This point here and this point here. They're on the same axis as the foci. So these are the what I call the major vertices. Most people just call them the vertices, but I call them the major vertices because they lie on something called the major axis. So the major vertices. And well, I'll just go ahead and say major vertices, and I'll point an arrow here, and I'll loop around and point an arrow there as well. Again, they're the vertices or the points on the ellipse that are of maximal distance away from the center. And you also have 2 points of minimal distance away from the center, and those are called the minor vertices. So let me go ahead and label those. These 2 points right here, this one up here, and this one down here, those are the minor vertices. Minor vertices. And again, those are not actually official definitions, although I don't know why they're not, because they should be. But the minor vertices are, in my opinion, are the points on the curve of minimal distance away from the center. Let's see, so we've just discussed this. The major vertices are the 2 points of greatest distance from the center. The line going through those vertices, and by virtue of just the picture that we can see below, the line that goes through those major vertices and therefore the foci in the center is called the major axis. So if I were to draw the major axis in here, which kind of would be a pain in the butt, but I did it, there we go. The line that goes through the 2 foci, the center, and the major vertices is called the major axis. And you have a line that goes through the center and the minor vertices, and that's called the minor axis. I'm just kind of scratching this out real quickly. Again, that line is called the minor axis. Now that is an official definition. So that finishes that paragraph right there. We have all those pieces defined, and you can see, by the way, in the picture down below, it gets real messy, doesn't it? The semi-major axis is the line segment from the center to either of the major vertices. So this is essentially a distance. It's that semi-major axis you may never have heard of. I only define it because I use that definition in a future theorem. Actually, in this definition right here, I can see it. So I'll show you where it is. But semi-major axis is basically the half length of the line segment from major vertex to major vertex. Or in other words, the semi-major axis is this distance between center and major vertex, or between center and major vertex. Doesn't matter. It's the same distance, either case. All right. So, and then the semi-minor axis, which I'm never really going to talk about, is from the center to the minor vertex distance. That's okay. We're not going to talk about that. So finally, the eccentricity of an ellipse. And eccentricities are actually not unique to ellipses. They actually belong to other conics as well. But the eccentricity of an ellipse is defined as the ratio of the positive distance from the center to either foci. So the ratio of, let me go ahead and showcase the distance I'm talking about. That C that I've just drawn in there right here, that distance C is the distance from the center to a foci. It's a positive distance is what we're going to call it, so that you can measure either from the center to the right focus or from the center to the left focus. We'll still have that distance be called as positive. Anyway, the eccentricity is the ratio of that distance to the semi-axis to the semi-major axis's length. So let me write that down, and I'm going to use black for that. The eccentricity, E, and by the way, most people actually use like a cursive E for eccentricity, is equal to that C over the length of this major axis, semi-major axis, sorry. So over the length of semi-major axis. Now you can probably tell right now there's a lot going on with an ellipse, and you spend about a day on them, which is very, very unfortunate because you just don't have a lot of time to go through all that stuff. A couple things I need to note here. The distances actually from the center to each major vertex and from the center to the minor vertices, that distance gets a very special label in this picture. The horizontal distance from the center to either of the vertices, major vertices, is called A, traditionally. And the distance along the semi-minor axis, or in other words, from the center to the minor vertex, is labeled as B, again, traditionally. Now, there are some adjustments that I would generally do to this. However, you're not one of my students, or you may not be one of my students. So because of that, I'm not going to adjust any of these definitions to fit my needs. Normally, when I redefine things, I redefine them to make sense. Calling that distance from the center to the to the vertex A carries no meaning to individuals. So if you were one of my students and I was just teaching this in a classroom, I would call this distance down here V sub X for the vertex in the X direction. And I would call this distance, this vertical distance, V sub Y, which is the vertex in the Y direction. That to me makes more sense than A and B. And unfortunately, most, in fact, all authors do not follow that convention. You'll be hard pressed to find a single author that does something like that. So that was the full definition of an ellipse and all the language we're going to use when we describe ellipses. Now we're going to talk about what is the equation of an ellipse, and this equation can be derived from the definition. Therefore, it is a theorem. So here is the theorem for the standard equation of an ellipse. The standard form of the equation of an ellipse with center at h comma k, that's very important, is x minus h quantity squared divided by that a squared, where a is the distance from the center to the major vertex, I should say from the center to the vertex in the x direction, plus the quantity y minus k squared over b squared, where b is the distance from the center to the vertex in the y direction. And then that is all equal to 1. And this would likely showcase why I prefer a different form of this equation that makes sense, I think, for most of us, which is, as long as you're not into the memorization, x minus h quantity squared over the vertex in the x direction squared. In other words, the distance to the vertex in the x direction squared, plus y minus k quantity squared divided by the distance to the vertex in the y direction squared is equal to 1. That to me just is a better definition here. Or a better build for this equation, I suppose. It's not that big of a deal. It doesn't actually matter which one you use, but I'm letting you know that is probably the one that I would prefer to work with. The rest of this sentence right here is just describing what I just said. The vertices along the horizontal axis of the ellipse are A units from the center, and the vertices along the vertical axis of the ellipse are B units from the center. The major axis is determined by the greater of A and B. And if you had you don't actually need to actually include this sentence in this theorem, because it is readily available from the sentence right here. It actually is true that if, let's just say, A is greater than B, then the vertices along the horizontal horizontal axis for the ellipse will be further away from the center, and so you have that major axis, remember, is the one with the greater distance. Anyhow, or you could just memorize that the major axis is determined by the greater of A or B. Finally, the foci are C units from the center, and that's by definition. Remember, our definition had the foci at C units from the center, and that distance C can be found using this relation. So we're going to derive that relation in the process of proving this equation, because a lot of people look at that relation and say, what? How did you get to that? And there is a very specific reason for that. One last thing I want to mention here, that relation that I've written there at the bottom, C squared is equal to the absolute value of A squared minus B squared, honestly is rarely written. In fact, I don't know very many textbooks that write that. However, this goes very nicely with the structure of how I teach hyperbolas. When this is a plus, I have c squared is equal to the absolute value of a squared minus b squared. If that was a minus here, then c squared would be the absolute value of a squared plus b squared, which you don't need the absolute values there, but whatever. Okay, so just to let you know, that's a convention that I use, mainly because it makes life easier for students. Now on we go to the proof itself. Now, before we begin the proof, I just want to say that we're going to prove this for h equals 0, k equals 0. We have to kind of all agree that because we've gone through all of algebra at this point, and conic sections are at the very end of algebra, honestly, that we know how to shift a figure by transformations. If you want to shift a figure horizontally, wherever its x value is in its formula, you will put a minus h, and that will shift it horizontally. We have seen that with something like, for example, y is equal to a times x plus or minus something squared plus k. If you put a minus h there, then it will shift things right or left. We know that from transformations. The same is true actually with y values. That if you had written, I should have kept that there, but if you had written that a times x minus h squared plus k, you could have moved the k to the other side and seen that that's y minus k is equal to a times x minus h quantity squared. If you change the value of h, the graph of that parabola will shift left or right. If you change the value of k, the graph of that parabola will shift up or down. So we should all be okay with the fact that when you have a group like this with y minus k or x minus h, that shifts your graph so many units left, right, up, or down. So that is where we're going to start, is with the assumption that we can just center this ellipse at 0 first, and then, or at the origin first, and then build from there. So there's my freehand drawing of an ellipse. Sorry that it's kind of messy. And then I'll place the foci just arbitrarily on the x-axis here. They don't need to be on the x-axis. I could have done this on the y-axis. It would just be a different shape slightly. It'd be slightly narrower, slightly taller, or something like that. But anyhow, we're gonna go ahead and place the foci on the x-axis there just for this proof. And I'll call this f sub 1 for the first foci and first focus, and f sub 2 for the second focus. And they're supposed to be c units away from the center, right? So this second focus should be at an x value of c, comma, and then the y value is 0. The first focus, way over here, should be at x equals negative c, y equals 0, right? Because it's c units away from the center. All right, so that is really where we kind of start our discussion. We're now going to just plot a point x comma y on our curve. Now remember, to build this ellipse, we would have a string of constant length attached to those two foci, and then you would pencil out this shape. So let's just pretend we've already done that, and remember that the string that connects between f sub 1 to any point on the curve and then to f sub 2, that string is of constant length. So this red string right here is of constant length no matter where I place that point. And we are going to call that distance of all that red string there, we're going to call that something very special. So let me go ahead and use some notation that you should have learned previously. The notation I'm going to use is just distance notation. So the distance between the first focus and the point P, so that's just this distance right here, plus the distance between the second focus and that point P. That should be constant no matter where we place the point P. And for convenience, because what we're going to do is use a value later on. So I'm going to just say this is some number. Normally you'd say like, oh, this is some number that is constant, right? We're going to call this number 2a. Now you don't know what a is. I haven't defined a on this picture yet. So if a is 0.1, then that distance will be twice 0.1 or 0.2, right? So I'm not really saying, I just need that 2a there for part of a proof. So it's still a constant. It's just some value. And you should recall from the distance formula, the distance between 2 points is just the square root of the sum of the squares of their distances between their x values and their y values. That is, the distance between the foci f sub 1, or the focus f sub 1, and the point P is just going to be the square root. This implies we have the square root of, let's take the distance between their x values. So x minus a negative c squared plus the distance between their y values, y minus 0 squared. And then the distance between the focus at f sub 2 and the point P is going to be the square root of, again, x minus the x value for f sub 2, which is c, squared, plus the distance between the y values, which is y minus 0 quantity squared. And we want that to be 2a. I'll clean this up just a little bit, not a lot. I like little baby steps here. So this is the square root of, this is going to be x plus c n quantity squared plus y squared, plus the square root of x minus c quantity squared plus y squared. And that's still just equal to a constant distance. Now we have spent quite some time in algebra up to this point solving equations and all different types of equations, but specifically radical equations. And this is definitely a radical equation here. So I'm going to isolate one of the radicals and square both sides. It actually does not matter which radical you isolate. So I'll go ahead and just isolate the radical. I'll isolate this guy. I'll just keep that guy on the left-hand side. So on the left-hand side, we have a square root of x minus c quantity squared plus y squared. And I'm subtracting the other square root to the other side. So that's 2a minus the square root of the quantity x plus c and quantity squared plus y squared. All I did was just move a radical to one side. That's it. Now I'm going to square both sides so that I at least get rid of this radical here. Squaring the left-hand side, I will get the quantity x minus c and quantity squared plus y squared. Squaring the right-hand side, that's a binomial. It's 2a minus something. And you're going to square that, so it'll be 2a minus something times 2a minus something, which is actually 4a squared minus 4a times that something. Let me get that isolated or written out here. And then plus that something squared, so plus this square root squared, which is going to be x plus c and quantity squared plus y squared. Now you can see this is a bit of a mess, but you can at least simplify this down a little bit. You don't have to go crazy here, but you can simplify it down a little bit. What I'm going to do, actually, I like to showcase some of this stuff. So what I'm going to do is move this radical piece, this term right here, to the left-hand side, and I'll move everything else to the right-hand side. So I have 4a root the x plus c and quantity squared plus y squared. And that is equal to, now, subtracting y squared from both sides. That's gone. And that 4a right there still remains, 4a squared, sorry, still remains on the right-hand side. I still have a plus x plus c quantity squared on this right-hand side. And, excuse me, I'm moving this x minus c quantity squared to the right-hand side with a subtraction. So minus x minus c quantity squared to the other side. We're going to clean that up. Now, there are a couple ways you can clean this up. Probably the one way that most people will go about cleaning up that right-hand side is by distributing things out, and you could totally do that, but I love to showcase kind of not shortcuts, but cool uses of things you've seen in the past. I hope you would agree that and that are both squares, and you have a difference of them. So this is actually a difference of squares. You could multiply them out. It's not that big of a deal. So what I'm about to do, you could do just by multiplying out and combining like terms. But I just like to showcase kind of some cool stuff. So I'm going to take that first picture, subtract the second picture, times the first picture, plus the second picture. Again, first squared minus last squared. It'd be first minus last times first plus last. So that's what I used there. Although, again, you could totally have multiplied that out. I just dig being able to do something like this because it's kind of cool. I don't know why. It just is. Okay. So let's see what we get here. On the right-hand side, we get 4a squared. The x's cancel. We have c minus negative c, so we have plus 2c. And then we have x plus x, so there's 2x there, and the c's cancel, so times 2x, but we know that's going to be 4cx. All right. So this is absolutely clean up to this point. Obviously, you could divide everything by 4, so I'm going to just magically erase, the 4s here, just so that I don't have to handwrite all that stuff again. And we do yet again another squaring of both sides to get rid of that last set of that last radical. Again, this is just from our skill set of solving radical equations. So squaring both sides, you get a squared times this x plus c squared plus y squared. On the right-hand side, when you square the right-hand side, you'll get an a to the 4th plus 2a squared cx plus c squared x squared. So a bit of a mess. Looks like you're not going to get very far if you keep it like this. We're going to distribute everything out on that left-hand side. So this will imply, I'm just going to quickly do the distribution. So we'll have an x squared times a squared x squared. We'll have a 2cx times a squared, so plus 2a squared cx. We'll have a c squared times a squared, so plus a squared times c squared. And then finally plus a squared y squared. Whoops, that's supposed to be a square. That's supposed to be a square. Is equal to a to the 4th plus 2a squared cx plus c squared x squared. And if you're following along up to this point, you could easily see this is an absolute mess. It does not look like you're going to get anywhere, but you can actually get someplace very nicely as long as you combine terms appropriately. So what I'm going to do is move all terms that have x's and y's to one side. All terms without x's and y's, I'll move to the other side. So go ahead and I will do that here. So this implies collecting stuff with x's, I get a squared x squared plus, let's see, 2a, actually I'll color code this. So in blue, a squared x squared plus 2a squared cx minus c squared x squared. Okay, so those are all the terms with x's. Oh, actually, minus, I just saw that 2a squared cx as well. So that gets rid of, moves all these things together. And by the way, you can see that 2a squared cx's will cancel beautifully. In green, I'll write everything with y's. So plus a squared y squared. Oh, that's it. That's everything with y's. And then on the right-hand side, I'll keep all the constants. So a to the 4th. I will also move this a squared c squared, so minus a squared c squared to the right hand side. Okay, so I hope that looks okay so far. Remember that 2a squared cx kills off the negative 2a squared cx. And so what I'm going to do is, out of those blue terms, I'm going to go ahead and factor the x squared out of them. So that would leave us with the quantity a squared minus c squared times x squared plus a squared y squared. And then on the right hand side, since both those terms have an a squared in common, I'll factor an a squared out, and we're left with an a squared minus c squared. We're getting very, very close here to the final form that we want to be in, although it's probably not super obvious to you. But what I'm going to do at this point is I'm going to go ahead and divide both sides by a squared times a squared minus c squared. Now, whenever you're doing a division that involves an unknown value, you want to make sure that that unknown value is non-zero. So let me justify why those values are not zero. First of all, a is not zero. We're going to be dividing by a squared right here. So a is not zero. How do I know a is not zero? Because twice a is that constant distance in red. So if a were zero, we're not drawing out an ellipse. There you go. A squared minus c squared, on the other hand, what the heck is that? Like, how can I guarantee that a squared minus c squared is non-zero? And this really is why we labeled our distance in red there to be 2a. Well, if you think about it, that leg of this triangle that we currently have, that distance is going to be less than the sum of those two red distances. So let me just say that this way. Remember, this distance right here is c, and this distance right here is also c. And the red distances, those add up to 2a. So the distance between, I'll just say it this way, between P and F1 plus the distance between P and F2. So in other words, all this red ink here, these distances, when you sum those up, those have to be greater than 2 C's. And that's because that 2C distance is one leg of the triangle. Even if it's the largest leg of the triangle, the fact that it's the triangle inequality, essentially, that two leg sides are always longer when you sum them up than a single leg distance. And we labeled this distance right here 2a, so we know that 2a is greater than 2c, or in other words, a is greater than c, which tells us that a squared is greater than c squared, which means a squared minus c squared is greater than 0, or better yet, it's just not 0. So that's the justification as to why a squared minus c squared, when we divide both sides of that equation by it, isn't a division by 0. So here we are, back here, we're going to go ahead and divide both sides by a squared times a squared minus c squared. Dividing both sides by that, well, this term right here, when you divide by a squared times the quantity a squared minus c squared, those a squareds minus c squareds will cancel, and you get x squared over a squared. Plus, when you divide the next term by a squared times a squared minus c squared, the a squareds cancel. You get y squared over a squared minus c squared. And of course, you're dividing the right-hand side by itself. That becomes the number 1. Now we're very close to the final statement. We'll just go ahead and let b squared equal a squared minus c squared. Now again, we don't know what b or a are right now. We just called twice a the distance of those red like strings when we added them up. So we still don't quite know geometrically, we don't know the roles that a and b will play, but at least we're just saying, hey, if I call a squared minus c squared the letter b squared, well, then this simplifies this formula to x squared over a squared plus y squared over b squared is equal to 1. And right now, as long as we have that initial statement that we all agreed with, which is that when you shift things left, right, up, or down, you're just putting a minus h and a minus k next to those y's and x's, that we now have essentially the equation of the ellipse. However, we do need to prove that the major, or the vertices in the horizontal and vertical directions are actually the A's and B's? Well, you could do that very easily if you say if x is equal to 0, in other words, we are on the y-axis, then you have, let's see, 0 squared over a squared, which is 0. You have y squared over b squared is equal to 1, or in other words, y is equal to plus or minus b. In other words, the point 0, the points, I should say, 0, plus or minus b are on our ellipse. So our arbitrary choice for calling that denominator right here b squared leads to the fact that b itself is a vertex in the vertical direction. It is a point on the curve, 0, plus or minus b. Those are points on the curve in the vertical direction. Likewise, if you were to say if y is equal to 0, well then, with the same argument, if you let y equal 0 in that equation above, you would get x is equal to plus or minus a. That is, the points plus or minus a comma 0 are on this curve. And so therefore, we now know, having gone through this entire derivation, that the equation of this ellipse right here is x squared over a squared plus y squared over b squared equals 1, where this point right here and this point right here are negative a comma 0 and positive a comma 0 respectively. And this point up here is 0 comma b, and this point down here is 0 comma negative b. Now the only other thing we need here is a relationship between a, b, and c, but we actually have that relationship down below. Let me showcase it here. This is the relationship between a, b, and c right here. And it turns out that I can write this as c squared is equal to a squared minus b squared. Let me write this here. I'll say this implies c squared is equal to a squared minus b squared. We now want to know, why is that absolute value there? When we derived this whole thing and we got to that bottom part where we said c squared, here it's right here, c squared is equal to a squared minus b squared, we didn't have absolute values on that. The reason I have absolute values on that is because if you do two derivations of this theorem, one for the horizontal axis being the major axis and one where the vertical axis is the major axis, they kind of involve different setups. The setup for the vertical axis being a major axis means that you're going to let that distance between the 2 points, this initial distance, you're going to let that be 2b. And that changes everything, well, changes something slightly. The thing that it changes is that in the end, b will be larger than a, and so b squared will be larger than a squared. And you'll end up, if you try to keep this without inequalities or without absolute values, you'll end up with this, which won't make sense because b squared will be greater than a squared, and that will be a negative number equaling c squared. That will not happen. Because you build it slightly differently when you have a vertical major axis, it would look like this. C squared is equal to b squared minus a squared for the vertical major axis. So instead of memorizing two of those, it's just much easier just to say, listen, c squared is equal to difference of the squares of a and b, and whichever one is larger, a or b, is written first. That's really the easiest way of saying that. So you'll see it in the examples that we do in the next video when we get to the example sets. Now I do know that this is generally a tough pill to swallow when you're first seeing ellipses. I'm assuming that you've played with ellipses before, so I'm not really assuming that you're super low level on this stuff. But if it is your first time dealing with ellipses, trust me, this is the worst that it gets right here. From this point forward, it gets a little bit easier, or in fact, a lot easier. All right, so in the next video, we'll start and we'll just run through a bunch of examples. And I think I have two videos, extra videos in the series, one for graphing ellipses and then one for finding equations of ellipses. So I'll see you in the next videos.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.